Welcome to the deep dive. You know that moment, maybe you're building an app or just casually using one, and you hit save or search. You tap that button, and instantly your data is just there. Your search results magically pop up on screen. It feels like this effortless, almost instantaneous exchange. But what actually happens behind the scenes, deep inside the database, to make that work? How does it manage to store your precious data and then find it again at lightning speed?
That's precisely the fascinating, often hidden world we're going to pull back the curtain on today. We're diving into the mechanics of database storage and retrieval. This is where your beautiful logical data models and your elegant SQL queries transform into physical bits and bytes on a disk or reside fluidly in memory. It's truly where the rubber meets the road.
And to really set the stage for this deep dive, I want to open with a classic German proverb that perfectly captures the fundamental tension at the heart of database design.
Wer Ordnung hält, ist nur zu faul zum Suchen. For those of us whose German is a little rusty, that translates to, if you keep things tidily ordered, you're just too lazy to go searching.
It's a fantastic proverb for our topic because it immediately highlights a core dilemma. As a designer of any storage system, you have a choice. Do you spend a lot of painstaking effort upfront, meticulously organizing every piece of data as it comes in? Or do you prioritize making retrieval blindingly fast, even if it means some underlying mess or duplication? Databases are constantly wrestling with this exact trade-off. It's a foundational decision that impacts everything from performance to complexity.
And our mission today is to give you a shortcut to truly understanding these foundational technologies that power virtually every application you interact with daily. You don't need to be a seasoned database administrator or even plan to build your own storage engine from scratch to profoundly benefit from this deep dive. Absolutely. This isn't just for the database gurus. This is about making you a more informed application developer, a more astute system architect, or even just a more curious technophile who can appreciate the clever engineering happening behind that save button. Knowing what's happening under the hood empowers you to ask better questions, to confidently interpret documentation, to choose the right tools for your specific application, and critically, to tune them for peak performance. It's invaluable knowledge that helps you troubleshoot and optimize when things aren't quite humming along.
Okay, let's unpack this core challenge of database storage and retrieval. At the most fundamental level, a database really has just two primary tasks.
Indeed. It needs to take the data you give it, whether it's a new user profile, a blog post, or maybe a financial transaction, and store it durably. And then at some later point, it needs to give that data back to you reliably and quickly when you ask for it. That's the essence of what a database does, stripped down to its bare minimum.
In our previous deep dives, we spent a lot of time discussing how you, the application developer, interact with the database. Defining data models, writing queries in languages like SQL or NoSQL. We talked about how you give data to the database and how you ask for it back.
Right. But today, we're shifting our perspective entirely. We're diving into the database's internal mechanics, its brain and its hands, if you will. How does it physically store that JSON document or that relational row you just inserted? And then when you execute a select statement, how does it efficiently find and retrieve that data from potentially vast amounts of stored information? It's the physical layer of data management that often goes unnoticed, but is absolutely crucial.
So to really illustrate this, let's imagine what is probably the absolute simplest database in the world. It's so simple we could implement it with just two basic bash script functions. Let's call them deepset and debigget.
Okay, the debootset function would be incredibly straightforward. Echo $1, $2 database. It takes a key, a value, separates them with a comma, and just appends the entire string to a file named database. That's it. Just writing to the very end of a single text file. Imagine how simple that is for the operating system and the disk.
And then dbgit is equally, well, elegant in its simplicity. grep $1, database set in its S1, tail, nash, and 1. This function uses grep to find every line that starts with your requested key. Then beebstead strips off the key itself, leaving just the value. And finally, tail, nash, and 1 picks the very last occurrence of that key in the file.
Let's actually see this in action. You could imagine running dbset 1, 2, 3, 4, 5, 6 name, London attractions, Big Ben, London Eye, then dbset 42 name, San Francisco attractions, Golden Gate Bridge. And if you then immediately run dbset 42, it would instantly return San Francisco attractions, Golden Gate Bridge. Seems to work perfectly, right?
It does. But here's where it gets really interesting. What happens if you want to update a key? So let's say you run dbset42 name, San Francisco attractions, exploratorium, because San Francisco got some new attractions. Now, if you dbget 42 again, you'll see the new value, San Francisco attractions, exploratorium.
Crucially, If you then just cat the raw database file, you'd see something like this.
London attractions, Big Ben, London
San
Eye,
Francisco attractions, Golden Gate Bridge, San Francisco attractions.
Exploratorium.
Notice that the old version of Key 42 is still right there in the file. The magic of tail Nyan1 in our DBIA command is precisely what ensures you always retrieve the latest value, even if there are multiple older entries for the same key. This append-only design, where you never overwrite existing data but just add new versions, is actually a very powerful and fundamental concept. Many real databases use this log idea.
A log. So you don't mean like an application log file for debugging. No, that's a different use of the word. Here, log just means an append-only sequence of records. It's often binary, not human-readable text, but the principle is the same. You only ever add to the end.
Okay, so this deceptively simple deep set function with its append-only mechanism actually has surprisingly good performance. Why is that? Because in a world where we're always told random access is fast, this seems to go against the grain.
That's a crucial insight. Appending to a file, essentially just writing to the very end of it, is fundamentally one of the most efficient operations for disk hardware. This is especially true on traditional spinning magnetic hard drives, where sequential writes allow the disk head to just keep moving in one direction without costly back-and-forth seeks. But even on modern solid-state drives, SSDs, sequential writes are generally preferable to random writes as they optimize the internal block management. This isn't just a minor optimization. It's a foundational insight that powers many of the fastest databases and storage systems today.
Okay, so DSET sounds like a hidden superstar. But what about deep set? This is where our simple database probably hits its wall, right?
Ugh. DBGIT is where the elegance truly breaks down. Its performance is terrible, particularly as the number of records grows. Every single time you want to look up a key, DBGIT has to scan the entire database file from beginning to end, line by line, looking for occurrences of that key. If your file has 1,000,000 lines, it checks 1,000,000 lines. If it has 1,000,000,000, it checks 1,000,000,000.
In algorithmic terms, we refer to that as an ON cost.
Yeah.
If you double the number of records N in your database, a lookup takes, on average, twice as long. That's simply not scalable for any real-world application, because real-world applications need to be fast, even with huge amounts of data.
Precisely. This scanning problem is the core challenge that needs solving for efficient data retrieval in any serious database. And the solution, as you've hinted, lies in something called an index.
An index. So it's like a library catalog, or to use a more modern analogy, maybe like the index in the back of a textbook. Right. It's an additional data structure that sits alongside your main data, specifically designed to help you locate what you want quickly without having to scan everything page by page.
Exactly. An index is derived from the primary data. It's not the primary data itself. Think of it as a secondary structure whose sole purpose is to speed up lookups. Most databases allow you to add or remove indexes from your tables, and this doesn't change the actual data, only how fast you can find it. You can imagine the impact this has on query performance for complex applications.
But there's always a trade-off, isn't there? Because maintaining these additional structures incurs overhead. It's like keeping that textbook index perfectly up to date every time you highlight a new fact.
Absolutely. While indexes dramatically speed up read queries, they inevitably slow down writes. Every time you write new data or update existing data, the index also needs to be updated to reflect those changes. It's a fundamental tension in storage systems. You gain on reads, but you pay a price on writes. It's a constant balancing act.
And this is precisely why, as an application developer or database administrator, you're often given the power to choose which columns or fields to index. It's not a one-size-fits-all solution. You have to understand your application's typical query patterns. Are you reading a lot or writing a lot? And decide where that balance between read performance and write overhead needs to be struck. This is a critical decision that impacts the entire performance profile of your application. So we've seen how deceptively powerful that simple append-only log concept is. But how do real-world databases built on this log philosophy actually manage to find your data quickly without scanning the whole file every time? That's where indexes truly come into play, starting with the simplest form, the hash index.
Hash indexes are conceptually very similar to hash maps or dictionaries that you find in almost every programming language. The core idea is brilliantly simple. Why not keep an in-memory hash map where each key points directly to a precise byte offset in that append-only data file we just talked about? This offset tells the database exactly where that key's value can be found on disk.
So if I'm understanding this, when a new key-value pair is appended to the data file, the in-memory hash map is simply updated with this new offset. And this works for both brand new keys and for updating existing ones, because the older versions are just ignored by the lookup process.
Exactly. To look up a value, the database uses the hash map to find the offset, then performs a single lightning-fast disk seek, essentially jumping directly to that location in the file, and reads the value. If that data is already in the operating system's file system cache, it doesn't even require physical disk I/O, making it astonishingly fast.
This sounds almost too simplistic to be practical in a serious database. What's the hidden complexity here, or is it genuinely that robust for certain scenarios?
Right, it's genuinely robust and widely used for specific scenarios. This simplistic approach is, for instance, essentially what Bitcask, the default storage engine in React, does. And it delivers high-performance reads and writes when the conditions are right. The beauty is its straightforwardness translates to speed.
So what are those right conditions? What kind of workload is this ideal for?
It's best suited for workloads where keys are updated frequently, but crucially, the total number of distinct keys isn't so enormous that the entire hash map can't fit comfortably into your available RAM. Think of a system tracking real-time sensor readings, where a sensor ID is the key and its latest reading is the value. Or, the classic example, a cat video URL as a key and its play count as the value. You're constantly updating the count, but the number of unique cat videos or sensors might be manageable enough for all those keys to live in memory.
That makes a lot of sense. But if the hash map must fit in RAM, that's a pretty significant limitation, isn't it? What happens if you have billions of unique keys?
Precisely. That's the primary constraint. If your dataset has a truly vast number of unique keys, this approach simply won't scale because you'd run out of memory for the index itself. Another limitation is that it's not efficient for range queries. You can't easily ask for all keys between kitty 0000000 and kitty 99999 using a hash map. You'd have to look up each individual key one by one, which quickly becomes ON, again, if your range is wide.
Okay, so if we're just appending to a file and this log keeps growing, how do we prevent the database from, well, growing infinitely and eventually running out of disk space? You can't just keep adding new versions of data forever.
That's a critical operational challenge. The solution is to conceptually break the append-only log into smaller, fixed-size segments. Once a segment file reaches a certain size, say a few gigabytes, you close it and start writing all new data to a new segment file. Then in the background, you perform compaction on these older segments.
So compaction, is that just a database's way of tidying up its room? Or is there more going on under the hood that makes it a sophisticated process?
It's definitely more than just tidying up. Compaction involves going through a segment and actively discarding any duplicate keys, keeping only the most recent update for each key. This is where the older versions of your data are finally thrown away. This process can significantly reduce the segment size, especially if keys are frequently overwritten.
And then you can merge these compacted segments.
Yes, exactly. You can merge several compacted segments together into a single, much smaller, merged segment. This merging process runs in a separate background thread, so your database can continue serving read and write requests uninterrupted. Once the merging is complete, read requests seamlessly switch over to using the new consolidated segment, and the old segments can be safely deleted from disk. Each segment effectively has its own in-memory hash table, and to find a key, the database checks the hash map of the most recent segment first. If the key isn't there, it checks the next most recent, and so on. Merging keeps the number of segments small, which is crucial for maintaining fast lookups.
It's a surprisingly robust and clever system, especially for something that started with such a simple deep set operation. But what about the nitty-gritty of making this work in a truly practical, production-grade database? Like, are they really just appending comma-separated values? And how do you handle deleting records?
Excellent questions. No, comma-separated values are terrible for production. They have issues with escaping special characters and are inefficient to parse. Real implementations use much more efficient binary file formats, typically with length prefix strings, so the system knows exactly how many bytes to read for each key and value without needing to parse or scan. As for deleting records, you append a special marker, often called a tombstone record, to the data file. During the compaction and merging process, this tombstone acts as a signal to the system that any previous values for that key should be discarded entirely.
And what about crashes? If your system suddenly goes down, you're going to lose that precious in-memory hash map, aren't you? That would mean a long, slow rebuild.
You're right, that's a critical point. To address crash recovery, systems like Bitcask don't just rely on the in-memory map. They store periodic snapshots of each segment's hash map on disk. This allows for much faster restoration into memory upon restart, avoiding the need to rescan the entire segment file. And to protect against corrupted data if a crash happens mid-append, checksums are used. If a record's checksum doesn't match, the system knows it's partially written or corrupted and simply ignores it.
And concurrency. If you have many users simultaneously writing and reading from the database, how do you manage that without things getting messy?
Concurrency controlled is actually one of the areas where this append-only model simplifies things significantly. A common choice is to have just one writer thread, since writes are strictly sequential appends to the current log segment. This eliminates a huge class of concurrency issues right off the bat. However, because segments are append-only and become immutable once they are closed and flushed, multiple readers can access them concurrently without issues, as the data they are reading will not suddenly change underneath them.
So this append-only approach seems counterintuitive at first. You'd think overwriting data in place would be more efficient, maybe faster, but you're saying there are distinct, even profound advantages to this log philosophy. What are they?
Absolutely. The advantages are quite significant and often surprising. Firstly, appending new data and merging segments are sequential write operations. This is dramatically faster than random writes, especially on traditional magnetic spinning hard drives, where the disk head has to physically move for each random write. Even on SSDs, while the performance gap is smaller, sequential writes are generally preferable and more efficient for the drive's internal wear leveling.
Okay, so it's a win for the underlying hardware. What else makes this approach so powerful?
Secondly, concurrency and crash recovery are significantly simpler when segment files are append-only and immutable. You don't have to worry about complex scenarios where a crash occurs mid-overwrite, potentially leaving you with corrupted data where old and new values are spliced together in a half-written state. The immutability of segments after they're written is a very powerful property, leading to more robust systems.
And fragmentation. That's a common issue that can degrade database performance over time.
Yes, the merging process elegantly avoids the problem of data files getting fragmented over time, which can plague overwrite-in-place systems and cause performance degradation as the data becomes scattered across the disk. Because LSM trees periodically rewrite segments, they consolidate data and remove dead space, keeping files compact and efficient.
So we've covered the basics of hash indexes and how log-structured storage handles growth through segments and compaction. But those hash indexes still have that limitation of requiring all keys to fit in memory, and they're not great for range queries. What's the next evolution in making this log-structured approach even more powerful and versatile?
That leads us directly to SS stables and LSM trees. The key innovation here is a simple but profound change. Instead of just having segments of arbitrary key-value pairs, we require that the sequence of key-value pairs within each segment is sorted by key. This sorted format is what we call a sorted string table, or SS stable.
So the files themselves are sorted now. How does that seemingly small change make such a huge difference?
SS stables offer several huge advantages. The most significant is the efficiency of merging segments, even if the files are larger than your available memory. It's conceptually identical to the merge-sort algorithm you might learn in a computer science class. You read the input files side by side, pick the lowest key from either file, and write it to a new merged output file. Since all the values in one input segment must be more recent than values in older segments, if the same key appears in multiple segments, you simply keep the value from the most recent segment. This means you only ever write the most up-to-date information, gracefully handling updates and deletions.
That's incredibly elegant. It turns a potential mess into a streamlined, sorted stream. What about finding a key? Do you still need that big in-memory index for every single key in an SS table?
No, and this is another major win for scalability. Because the data within an SS table is sorted, you no longer need to keep an index of all keys in memory. You only need a sparse in-memory index. For example, you might store the offset for just one key every few kilobytes of the segment file. If you're looking for handiwork and you know your sparse index has pointers for handbag and handsome, you can jump to the block containing handbag and then just scan a small portion of the file from there to find handiwork quickly. A few kilobytes can be scanned very quickly by the disk and the CPU.
And compression, I imagine, would be fantastic with sorted data.
Absolutely phenomenal. Since read requests often scan over ranges of key value pairs and the data is sorted, you'll find long runs of similar values. You can group those records into a block and compress it before writing it to disk. Each entry in your sparse in-memory index then points to the start of a compressed block. This not only saves massive amounts of disk space, but also significantly reduces the amount of I/O bandwidth required to read data, as the database is moving much less data across the wire.
So how do you actually construct and maintain these SS stables if incoming writes can occur in any order? You can't just append them to an already sorted file without resorting everything. That sounds expensive.
You've hit on the core of the LSM tree algorithm. When a write comes in, it's not immediately written to an SS stable. Instead, it's added to an in-memory balanced tree data structure, most commonly a red-black tree or an AVL tree. This in-memory structure is called a mem table. Its job is to keep the data sorted in memory as new writes arrive.
And then when that mem table gets full, it gets written to disk as a new SS stable.
Exactly. When the mem table reaches a certain size threshold, typically a few megabytes, it's efficiently written out to disk as a brand new sorted SS stable file. This newly created SS stable becomes the most recent on-disk segment. While that's happening, new incoming writes can immediately continue to a new empty memtable instance, ensuring the system remains continually available and responsive.
So for a read, you check the current mem table first, then the most recent on-disk SS stable, and then progressively older SS stables until you find the key or confirm its absence.
That's the read process, and from time to time, a continuous background process runs to merge and compact these various SS stable segment files. This process combines files, removes old or deleted values, and produces larger, more optimized SS stables. It's crucial for keeping the number of segments manageable and ensuring disk space doesn't grow indefinitely. Now, the only remaining problem here is data loss if the database crashes before the memtable is successfully written to disk.
The durability problem resurfaces. How is that handled to prevent losing recent writes?
To solve that, you introduce a separate unsorted write-ahead log, or wall, on disk. Every write is immediately appended to this wall before it's even put into the mem table. Its sole purpose is to act as a safety net. If the database crashes, this log is used to restore the mem table to its state just before the crash. Once the mem table is successfully flushed and written to an S table on disk, the corresponding portion of the wall can be safely discarded. So the disk is always the ultimate source of truth, even for in-memory operations.
This entire scheme sounds remarkably sophisticated, and I know it's fundamental to some very big names in the database world.
It is. This algorithm is essentially what's used in LevelDB and RocksDB, which are popular embedded key-value storage engine libraries. It's also foundational to distributed NoSQL systems like Apache Cassandra and Apache HBase, both of which were inspired by Google's Bigtable, a pioneering system that coined the terms SS stable and memtable. Even Lucene, the underlying engine for full-text search systems like Elasticsearch and Solr, uses a very similar method for its term dictionary, where words are keys and values are lists of document IDs.
That's a powerful pedigree. But you mentioned reading a key might involve checking multiple segments. How do they handle queries for keys that don't exist? Like if you ask for a key and it's not in the mem table and you have to go through several segments on disk just to confirm its absence, that sounds like it could be slow and wasteful.
That's a great observation, and it's a real problem. To optimize for lookups of non-existent keys, storage engines often use a clever probabilistic data structure called a Bloom filter. Imagine it like a quick, fuzzy pre-check. It can tell you with very high certainty if a key definitely does not appear in a specific SS stable. It does this by running the key through a set of hash functions and checking corresponding bits in a bit array. If the Bloom filter says no, the database saves many unnecessary expensive disk reads to that segment. It's not perfect. It can sometimes say, maybe it's here when it's not, a false positive, but it never says it's not here when it actually is, making it incredibly useful for speeding up negative lookups.
And are all compaction strategies the same?
Yeah.
Or do different LSM tree implementations handle that background merging differently?
There are different approaches, and they significantly impact performance characteristics. The two most common are size-tiered and leveled compaction. In size-tiered compaction, which HBase often uses, smaller, newer S-stables are merged into larger, older ones. In contrast, LevelDB and RocksDB typically use leveled compaction, which splits key ranges into smaller SS stables and organizes them into distinct levels. This allows for more incremental, smaller compactions and often uses less disk space, but can be more complex to manage. Cassandra actually supports both, allowing you to choose based on your workload.
So Even with those nuances, the basic idea of LSM trees, a cascade of S tables that are kept sorted and merged in the background, is incredibly simple, yet effective. It works well even for datasets much bigger than available memory, allows for efficient range queries because the data is sorted, and can support remarkably high write throughput due to those sequential disk writes.
Precisely. It's a very powerful and increasingly popular paradigm in modern database design.
All right, so we've spent a good chunk of time on log-structured storage engines. But as you mentioned earlier, they aren't the most common type of index, at least historically. That title belongs to the B tree. Let's explore B trees now, which represent a very different design philosophy. The override in place standard.
B-trees are truly ubiquitous. They were first introduced back in 1970, and they have not only stood the test of time but have evolved to remain the standard index implementation in almost all relational databases. Think PostgreSQL, MySQL, SQL Server, and many NoSQL databases also use them internally. Their longevity speaks volumes about their robustness.
What's the fundamental difference in their design philosophy compared to LSM trees, which are all about append-only logs and segments?
Unlike LSM trees, which break the database into variable-sized segments and write them sequentially, B trees break the database into much smaller, fixed-size blocks or pages. Traditionally, these pages are 4 KOB in size, though they can be larger. The fundamental operation for a B tree is to read or write one page at a time, a design that aligns very closely with how underlying disk hardware is structured, particularly older spinning disks.
And how do these individual pages come together to form a tree structure that allows for fast lookups?
Each page is identified by its address or physical location on disk. These addresses act like pointers, allowing one page to refer to another, forming a hierarchical tree structure. You start your lookup at the root page, which is the entry point for all searches. This root page doesn't contain actual data values, but rather several keys and references or pointers to its child pages. Each child page is responsible for a continuous range of keys, and the keys within the parent page act as the boundaries or signposts for those ranges.
So I'm looking for a specific key, say 251. How would that search process work through the B tree?
Okay. You'd start at the root page. You'd quickly scan the keys on that page to determine which child page's range contains 251. Let's say you find a reference that covers the range 200 to 300. You then follow that reference, loading the relevant child page into memory. That child page might further break down the 200-300 range into subranges, say 200-250 and 251-300. You continue traversing down the tree, following the appropriate page references based on your key's value, until you eventually reach a leaf page. The leaf page is special because it contains either the actual value for your key directly inline or a reference to where the value is stored elsewhere in the database.
How many levels deep does such a tree usually get? Sounds like it could be a very tall tree if there's a lot of data.
That's where the branching factor comes in. This is the number of references to child pages that can be stored within one single page. With 4 KLB pages, a B tree can typically have a branching factor of several hundreds, sometimes even thousands. This large branching factor means that B trees remain remarkably shallow, even for enormous data sets. Most databases can fit into a B tree that's only 3 or 4 levels deep. For instance, a 4-level tree with 4 KOB pages and a branching factor of 500 can theoretically store up to 250 terabytes of data, yet only require 4 disk seeks to find any specific piece of information. This logarithmic depth, often denoted as O log n, is precisely why B-tree lookups are so consistently fast.
What happens when you update an existing key or insert a new one into a B tree? It seems more complicated than just appending to a file.
When you update an existing key, the process is quite direct. You find the leaf page containing it, change the value, and then overwrite that specific page back on disk in its original location. The physical location of the page doesn't change, so any references to it from parent pages remain perfectly valid. If you insert a new key, you find the page whose key range encompasses the new key and attempt to add it there. If that page is already full, the B tree performs a crucial operation. It splits the full page into 2 half-full pages. Then, the parent page is updated to reflect this new subdivision of key ranges, adding new references that point to the 2 new child pages. This splitting and balancing mechanism is what ensures the tree always remains balanced and shallow, maintaining its O log n lookup performance.
So the fundamental write operation in a B tree is overwriting a page in place. This sounds inherently riskier and more complex to manage reliably than the append-only approach of LSM trees, especially if a crash happens during an update.
You're absolutely right to flag that as a potential challenge. Overwriting a page on disk, particularly for older magnetic hard drives, means physically moving the disk head to a specific sector and overwriting it. On SSDs, while it's much faster, it's still a complex process involving internal block erasures and rewrites. And crucially, some B-tree operations, like splitting a page, require overwriting multiple different pages. You have to write the two new child pages and then update their parent page.
That sounds like a recipe for disaster if a crash happens halfway through that multi-page operation. You could end up with an inconsistent state or even corrupted data.
It definitely can be. If the database crashes after only some of those pages have been written, you could end up with a corrupted index, for instance, an orphan page that no longer has a parent pointing to it, making some data permanently inaccessible. To make B-trees resilient to crashes and ensure atomicity, an additional data structure is universally employed. The write-ahead log, or WALL, also often called a redo log.
The wall sounds conceptually similar to what LSM trees use for durability. Are they essentially the same mechanism, or are there subtle but important differences given the distinct storage philosophies?
They are similar in purpose but differ in application. The wall in a B-tree system is also an append-only file. The critical rule is this. Every B-tree modification must first be written to this wall before it's actually applied to the pages of the tree itself. If the database crashes, this log is then used to restore the B-tree to a consistent state upon restart by replaying the uncommitted changes. With LSM trees, the wall primarily serves to recover the memtable if it hasn't been flushed. With B-trees, it ensures the integrity of the on-disk tree structure itself.
And what about concurrency control when multiple threads are trying to access and modify the B tree simultaneously? That sounds even more challenging with in-place overwrites.
Overwriting pages in place indeed requires very careful concurrency control. You need to prevent a thread from seeing the tree in an inconsistent, half-modified state during an update. This is typically done by protecting the tree's internal data structures with what are called latches, which are like very fast, lightweight locks. They ensure that only one operation is actively modifying a specific part of the tree at any given moment, keeping everything consistent. This is generally more complex to implement than in log-structured approaches, where all merging happens in the background on immutable segments, and old segments are atomically swapped for new ones, minimizing interference with live queries.
B trees have been around for over 50 years. I imagine there have been a lot of sophisticated optimizations developed over that time.
Decades of research have indeed led to countless improvements and variations. For example, some databases, like LMDB, use a copy-on-write scheme instead of overwriting pages and relying solely on a wall. When a page is modified, it's written to a new location on disk, and new versions of its parent pages are created to point to this new location. This simplifies certain aspects of crash recovery and concurrency control.
Interesting. What other clever tricks have they come up with?
You can save significant space within pages by only storing key abbreviations, just enough of the key information to define the boundaries between key ranges. This allows more key references to fit on a single page, increasing the branching factor and further reducing the tree's depth, which in turn reduces disk seeks. Also, while B-tree pages can theoretically be anywhere on disk, implementations often try very hard to lay out leaf pages sequentially on disk to improve range scan performance. However, maintaining this perfect sequential order as the tree grows and splits is incredibly challenging. By contrast, LSM trees naturally keep sequential keys together during their merging process, which is one of their inherent advantages for range reads.
And more pointers.
Yes, additional pointers can be added, such as sibling pointers between leaf pages. This allows for efficient standing of keys in order without having to jump back up to parent pages and then down again for the next key. And some B-tree variants, like fractal trees, even borrow ideas from log-structured designs to reduce the number of random disk seeks by buffering changes in a tree-like structure before flushing them to disk. It's a constant cross-pollination of ideas.
Okay, so we've got these two major philosophies for OLTP storage.
Yeah.
The log-structured append-only approach, LSM trees, SS tables, and the page-oriented overwrite-in-place approach, B trees. This is the great divide in database storage engines. What's the general rule of thumb for comparing them, and what are the crucial nuances?
As a very general rule of thumb, LSM trees are often cited as being faster for writes, and B trees are often thought to be faster for reads. However, it's absolutely crucial to qualify this immediately. Benchmarks are incredibly sensitive to the specific workload details, hardware, and configuration. Empirical testing with your specific workload is always necessary to make a valid comparison. For example, LSM tree reads can sometimes be slower because they often have to check several different data structures, the memtable, and multiple on-disk SS tables across various stages of compaction to find the most recent value for a key.
Let's talk about the advantages of LSM trees first. What makes them so good for writes, despite the fact that data gets rewritten multiple times during compaction?
One key concept here is write amplification. This refers to how many physical writes to disk a single logical write to the database actually generates over the database's lifetime. In B trees, a logical write typically leads to data being written at least twice, once to the write-ahead log for durability, and then once more to the tree page itself. There's also overhead from writing entire fixed-size pages, even if only a few bytes changed. Some B tree engines even overwrite a page twice for crash safety.
In LSM trees, how do they stack up on write amplification?
Log-structured indexes also rewrite data multiple times due to repeated compaction and merging of SS stables. However, LSM trees often achieve higher write throughput, partly because they can, in certain configurations and workloads, have lower write amplification overall. But the primary reason for their higher write throughput is that they predominantly perform sequential writes of compact SS stable files, as opposed to the more random, in-place overwrites of B trees. This sequential write pattern, as we discussed, is especially advantageous on older magnetic hard drives where sequential writes are orders of magnitude faster than random writes, but it's still beneficial for SSDs too.
What about storage efficiency and fragmentation?
LSM trees can generally achieve much better compression and often result in smaller files on disk compared to B trees. B tree storage engines, by their nature, tend to leave some disk space unused due to internal fragmentation when pages split or when rows can't fit into existing pages. Since LSM trees are not page-oriented and periodically rewrite SS stables to remove fragmentation, they usually have lower storage overheads, particularly when using advanced strategies like leveled compaction, which is designed to keep data compact.
And how does this play out on modern SSDs, which already have their own internal log-structured algorithms?
Even though SSD firmware internally uses a log-structured algorithm to turn the random writes it receives from the OS into sequential writes on the underlying flash chips, lower write amplification and reduced fragmentation from the database layer itself are still beneficial. Representing data more compactly at the database level allows more read and write requests to be processed within the available I/O bandwidth of the SSD, meaning you get more operations per second from your expensive hardware.
So LSM trees sound pretty great, especially for high-write workloads. But what are their downsides? There must be some trade-offs.
There are. One significant downside is that the background compaction process, while essential, can occasionally interfere with the performance of ongoing reads and writes. Even though engines are designed to perform compaction incrementally, disks have finite resources. A foreground request might, in some rare cases, have to wait for an expensive compaction operation to finish or compete for disk I/O. While the impact on average throughput and response time is usually small, at higher percentiles, meaning those occasional but very slow queries that frustrate users, the response time of LSM tree-based systems can sometimes be quite high, whereas B trees tend to be more predictable and have lower tail latencies. This can be a real headache for developers building user-facing systems.
That sounds like a potential issue for user-facing applications where consistent, predictable latency is critical. What if the database just can't keep up with the writes?
Exactly. Another critical issue arises at very high write throughput. The disk's finite write bandwidth must be shared between the initial incoming writes, which go to the WAL and MEN tables, and the background compaction threads. If compaction cannot keep up with the rate of incoming writes, the number of unmerged segments on disk will keep growing indefinitely. This can lead to running out of disk space surprisingly quickly and a significant slowdown in read queries, as they have to check more and more segment files to find the latest version of data. Often, LSM tree-based engines don't automatically throttle incoming writes, even if compaction is falling behind, so explicit monitoring and proactive management are crucial to prevent an outage.
And what about transactional guarantees? That's a huge deal for many databases, especially relational ones.
It is. A key advantage of B trees is that each key exists in exactly one canonical place within the index structure. In contrast, an LSM tree storage engine might have multiple copies of the same key spread across different segments, the MEM table and several SS tables. This single location property of B trees makes them very attractive for databases that offer strong transactional semantics. Many relational databases implement transaction isolation using locks on ranges of keys, and in a B tree, those locks can be directly attached to specific parts of the tree, simplifying the complex consistency mechanisms required for multi-statement transactions.
So to sum up this fascinating comparison, B trees are deeply ingrained, incredibly reliable, and have decades of optimization behind them, so they're definitely not going anywhere. But LSM trees are rapidly gaining popularity in new data stores and distributed systems, especially where sheer write throughput and massive scale are paramount.
Precisely. There's no universal best choice. The optimal storage engine truly depends on your specific use case, your workload patterns, and as we keep emphasizing, empirical testing of your actual application and data will always provide the most definitive answer. It's a dynamic landscape where both approaches continue to evolve.
So far, we've mostly discussed key value indexes, which are often used for primary keys of the unique identifiers for a row or document. But real-world applications rarely search data in just one way. You need to find users by their email or orders by their creation date, not just their primary ID. How do databases handle those more flexible searches? That's where we need to look at other indexing structures.
Indeed. Secondary indexes are incredibly common and absolutely crucial for flexible and efficient querying. In relational databases, you can create multiple secondary indexes on a single table. They are vital not just for ad hoc searches, but also for efficient joins between tables. For instance, if you have a large orders table and you frequently need to find all orders placed by a particular customer ID, you definitely want a secondary index on that customer ID column.
How do you build a secondary index from the core key value index concept we've been discussing?
It's quite straightforward. The main conceptual difference is that values in a secondary index are not necessarily unique. Many rows might share the same index value, for example. Many customers might order apples. You can handle this in two primary ways. Either the value in the index is a list of matching row identifiers similar to a postings list in full-text search, where apples points to row AD1, row D5, row D12, or you make each entry unique by appending the row identifier to the key itself, like apples row D1, apples row D5. Both B-trees and log-structured indexes can seamlessly serve as the underlying structure for these secondary indexes.
Now, when we talk about what's in the index, is it always just a pointer or reference to the actual row data elsewhere? Or can the data itself sometimes be stored directly within the index?
Not always just a pointer. The key in an index is what you search for, but the value can be one of two things. It could be a simple reference, a pointer, to the actual row data stored elsewhere, or it could be the actual row data itself. When the data is stored separately from the index, that location is often called a heap file, which typically stores data in no particular order.
What are the pros and cons of that heap file approach where the index just points to data elsewhere?
The main advantage is that it avoids duplicating data when you have multiple secondary indexes. Each index just points to a single location in the heap file where the actual data is kept. This saves space and simplifies updates to the data itself, as only the heap file needs to be changed. However, a significant drawback is that it requires an extra hop, an additional disk read, to retrieve the actual data after the index lookup, which can introduce a performance penalty during reads. Updating values in the heap file, especially if the new value is larger, can also be complicated, potentially requiring the data to move and all associated indexes to update their pointers. Sometimes databases will leave forwarding pointers, essentially a little note saying, "I moved over here," but that just adds another lookup step, further reducing performance.
So, to avoid that extra hop and speed up reads, there's another approach, the clustered index.
Exactly. A clustered index fundamentally changes how the data is stored. It means the actual row data is stored directly within the index structure itself, ordered by the primary key. MySQL's InnoDB storage engine, for example, always uses a clustered index for its primary keys, meaning your data is your primary key index. In SQL Server, you can specify one clustered index per table.
That sounds significantly faster for reads. What are the trade-offs there?
It definitely eliminates that extra hop, making reads for queries covered by the clustered index incredibly fast, as the data is right there. However, the trade-offs are significant. If you want to index by other columns, any secondary indexes on a cluster table will actually refer to the primary key value, not the physical location. So a secondary index lookup might first find the primary key and then use the primary key to find the actual data in the clustered index. This effectively reintroduces an extra hop. You also have higher storage overhead due to data duplication if you need other clustered-like indexes, increased write overhead as updates need to modify not just the index, but also the actual data embedded within it, and it complicates transactional guarantees because of that data duplication.
Is there a middle ground between always pointing to a heap file and fully clustering all the data?
Yes, there's a very practical compromise called a covering index or an index with included columns. This is where some of the table's non-key columns are stored directly within the index alongside the key. This allows certain queries to be answered solely from the index without needing to access the full row data from the heap file. It offers many of the read performance benefits of a clustered index for specific queries, but without the full duplication overhead or the complexities of a truly clustered primary key.
We've been talking primarily about indexing single keys or single columns, but what if you need to query multiple columns simultaneously? Like finding a user based on their last name and their first name. A single index wouldn't cut it.
Precisely. That's where multi-column indexes come in. The most common type is a concatenated index, sometimes called a composite index. This simply combines several fields into a single key by appending one column to another. For example, an index on last name, first name. This is highly efficient for queries on the full concatenated key or, crucially, on a prefix of the key. So finding all people with a particular last name, where last name Smith, or a particular last name and first name where last name Smith and first name John would be very fast.
But I'm guessing it wouldn't help if I only wanted to find people by their first name, where first name John.
You're exactly right. The database wouldn't be able to use the last name first name index efficiently for a query that only involves the later parts of the concatenated key, such as just first name. For that, you'd need a separate index specifically on first name.
So what about something even more complex, like geospatial data? If I'm trying to find all restaurants within a specific rectangular area on a map, that's a two-dimensional range query involving both latitude and longitude simultaneously. A standard B tree, which orders data linearly, wouldn't be able to handle that efficiently, would it?
Exactly. A regular B tree or LSM tree index could efficiently find all restaurants within a range of latitudes, or a range of longitudes, but not both simultaneously and efficiently. To solve this, you typically use one of two main approaches. You could flatten the two-dimensional location into a single number using a space-filling curve, like a Z-order curve, and then index that single number with a regular B tree. Or, more commonly, specialized spatial indexes like R trees are used. PostGIS, for example, a popular extension for PostgreSQL, uses R trees internally for geospatial queries.
And this idea of multidimensional indexes isn't just for geography, is it? It sounds like it has broader applications.
Absolutely. It applies much more broadly. Imagine an e-commerce site wanting to search for products within a certain range of colors, defined by red, green, and blue values. That's a three-dimensional range query. Or a large weather database where you want to find all observations within a specific date range and a specific temperature range. A multi-dimensional index could narrow down the search by all these criteria simultaneously, offering significant efficiency gains over searching on one dimension and then filtering the results. Some specialized databases, like Hyperdex, are built fundamentally around these multidimensional indexes.
And then there's the truly fuzzy stuff.
Yeah,
Full text search, my index isn't going to help me if I type Appel instead of Apple, or if I search for running and want ran or runner
yeah,
to show up right.
correct. Exact match or simple range queries don't cut it for similar T's, misspelled words, or linguistic variations. Full-text search engines need entirely different techniques. They deal with synonyms, grammatical variations, stemming and lemmatization, and finding words that appear near each other within a document. For typos, engines like Lucene, which powers Elasticsearch and Solr, can search for words within a certain edit distance. For example, one letter added, removed, or replaced.
How does Lucene accomplish that fuzzy search? Does it also use these SS-stable-like structures we discussed?
Yes, Lucene uses an SS-stable-like structure for its term dictionary, where the key is a word and the value is a list of documents containing that word. While LevelDB uses a sparse collection of keys for its in-memory index, Lucene takes it a step further. It organizes its term dictionary using a finite state automaton over the characters in the keys, similar to a trie data structure. This automaton can then be transformed on the fly into a Levenshtein automaton, which enables incredibly efficient searching for words within a given edit distance. It's essentially a highly optimized dynamic dictionary that can intelligently adapt to small errors or variations, allowing for lightning-fast fuzzy matching across huge corpuses of text. This is a fascinating area that continues to evolve, extending into document classification and sophisticated machine learning applications.
We spent a lot of time talking about storing data on disks. But disks, for all their durability and low cost per gigabyte, are, well, awkward for performance compared to RAM. So what happens when you decide to keep everything in memory? That brings us to in-memory databases.
As RAM gets cheaper and cheaper, and applications demand ever lower latency, it's becoming entirely feasible to keep entire datasets, or at least the actively used portions in memory, sometimes distributed across several machines. This trend has led to the significant rise in popularity of in-memory databases.
But if the power goes out, all that data in RAM is gone, right? How do these databases achieve durability without disks being the primary storage.
That's the core challenge, and it's vital to distinguish between a simple in-memory cache, like memcached, where data loss on restart is acceptable, and a durable in-memory database like FultDB, MemSQL, Oracle Times 10, Redis, or Couchbase. To achieve durability, these systems employ various techniques. Some use specialized hardware, like battery-powered RAM modules that can dump contents to disk on power loss. More commonly, they write a continuous log of changes to disk, take periodic snapshots of the entire in-memory state to disk, or replicate the in-memory state to other machines for redundancy.
So even though they're called in-memory databases, they still interact with disk for durability and safety. The disk isn't completely out of the picture.
Exactly. The disk is primarily used as an append-only log for durability or for snapshots, but the vast majority of reads and writes are served directly from memory. This hybrid approach also offers operational advantages. Disk files are often easier to back up, inspect, and analyze using external utilities compared to raw RAM dumps.
So what's the true deeper performance advantage then?
hmm
Because a disk-based database with enough RAM will also cache frequently accessed data in memory, essentially avoiding disk reads for hot data. Where's the real game changer for in-memory databases?
That's a common and very insightful misconception. You're right, modern operating systems are already caching frequently used disk blocks in memory for disk-based databases if you have enough RAM. The true game changer for in-memory databases is that they can ditch the entire translation layer that disk-based databases require. They're not just avoiding disk, they're optimizing for the CPU. They can work directly with RAM-optimized data structures like native C++ objects or highly specialized tree structures that are much faster and more efficient for CPU access and manipulation. A disk-based database, even with caching, still has to take its in-memory representation and encode it into a format suitable for writing to disk, PG pages for B trees or stables for LSM trees, and then decode it back into memory on read. In-memory databases largely bypass this costly encoding-decoding overhead, which is where their real performance edge lies.
And I imagine this direct-to-RAM approach also opens up possibilities for unique data models and functionalities that would be difficult to implement efficiently on disk.
Absolutely. Take Redis, for example. It's famous for offering a database-like interface to complex data structures like priority queues, geospatial indexes, and sets, all operating in memory. Because all data is kept directly in memory, implementing these structures directly and ensuring their efficient manipulation becomes comparatively simple, allowing for highly specialized and performant operations that would be much more cumbersome or slower to build on top of a traditional disk-based storage engine.
What about future directions? Can in-memory databases support data sets larger than available memory without going back to all those disk-centric overheads?
Research into concepts like anti-caching aims to do just that. It works by intelligently evicting the least recently used data from memory to disk when memory runs low and loading it back when accessed again. This is similar to how operating systems handle virtual memory, but it's applied at a more granular record level within the database itself, allowing the database to manage memory pages more efficiently. However, a key requirement is that the indexes themselves must still fit entirely in memory, as navigating a large on-disk index would negate many of the performance benefits. Looking further ahead, new technologies like non-volatile memory, or NVM, think of it as memory that's nearly as fast as RAM, but retains its data even when the power goes out, are poised to significantly change storage engine design, potentially blurring these lines even further between memory and storage.
So we've explored the fundamental ways databases store and retrieve data. Now let's tie this back to real-world usage patterns, because databases aren't used for just one thing, right? There are very different types of workloads they need to handle.
Precisely. Historically, the term transaction originally referred to business transactions, like a sale or an order in a store. Over time, in database contexts, it expanded to mean any logical unit of reads and writes that needs to be treated as a single atomic operation. It's important to note this doesn't strictly imply all the ACD properties, which is a topic for another deep dive. Here, it simply means enabling clients to make low-latency reads and writes as opposed to periodic batch processing.
And this leads us to online transaction processing, or OLTP.
OLTP systems are the workhorses behind most user-facing applications. Think of your e-commerce websites, banking apps, social media feeds, online gaming. They're characterized by handling a very high volume of requests, but each request typically touches only a small number of records, which are almost always looked up by a unique key using an index. Records are frequently inserted or updated based on direct user input. The bottleneck in these systems is typically disk seek time, how fast the database can jump to specific locations on disk to retrieve or update individual records.
Then we have online analytic processing, or OLA. This sounds like the other side of the coin, a completely different beast.
It is. OLA systems are designed for business intelligence, reporting, and decision support, typically used by data analysts or business intelligence tools, not directly by end users. They handle a much lower volume of queries compared to OLTP, but each query is very demanding. Instead of looking up a few records by key, OLAP queries scan huge numbers of records, often reading only a few specific columns per record, and then calculate aggregate statistics like sums, counts, averages, or complex statistical distributions.
So for example, an OLAP query would be something like, what was the total revenue of each of our stores last quarter, broken down by product category? Or how many more bananas than usual did we sell during our latest promotion compared to the same period last year?
Precisely. These queries aim to provide deep insights and feed into reports for strategic business decisions, often looking at historical trends. The bottleneck in OLAP systems shifts dramatically from disk seek time to disk bandwidth, how quickly you can strum massive amounts of data from storage into memory and process it.
So given these two distinct purposes, what are the key differences then between OLTP and OLAP systems from a database perspective?
We can map out some critical distinctions. For OLTP, the main read pattern is fetching a small number of records by key, requiring low latency. For OLP, it's aggregating over a massive number of records, often involving complex calculations. OLTP systems deal with random access, low latency writes driven by user input, while OLP systems typically involve large-scale bulk imports or continuous event streams from various sources. OLTP is primarily used by end users and customers interacting with an application, while OLAP is for internal analysts and data scientists focused on decision support.
The data itself and its scale.
OLTP systems generally represent the latest current state of the data, what's happening right now. OLP systems, on the other hand, focus on the comprehensive history of events that happened over time, often immutable records. And finally, the dataset sizes differ significantly. OLTP databases typically range from gigabytes to terabytes, whereas OLAP databases, particularly data warehouses, are often orders of magnitude larger, easily reaching terabytes to petabytes.
So these are clearly very different beasts, optimized for different goals. Did they always use different databases?
Initially, no. In the early days of databases, the same systems attempted to handle both types of workloads. SQL was flexible enough to write both transactional and analytical queries, but by the late 1980s and early 1990s, as data volumes exploded and performance demands grew, companies began explicitly separating their OLTP and OLAP workloads onto different specialized databases. This gave rise to the concept of the data warehouse.
That's where we get into data warehousing. Why did this separation happen? Why couldn't analysts just query the main live OLTP database directly for their reports? It seems simpler to have all the data in one place.
The problem is that ad hoc analytic queries are often incredibly resource-intensive. They typically involve scanning large parts of the dataset, performing complex aggregations, and consuming significant CPU and I/O resources. Running these heavy queries directly on the live, user-facing OLTP system would significantly harm the performance of critical low-latency transactional operations. Imagine a website where checking out takes 30 seconds because an analyst is running a huge report in the background. Database administrators closely guard their OLTP databases for this very reason. They simply can't afford that kind of performance degradation for their operational systems.
So the data warehouse became the elegant solution to this conflict.
Yes. A data warehouse is a separate, dedicated, and typically read-only database specifically designed and optimized for analytics. Its content is a copy of data extracted from all the various operational OLTP systems across an enterprise, think customer-facing websites, point-of-sale systems, inventory management, human resources, supply chain, you name it. It consolidates all this disparate data into a single, unified view.
And how does all that data get into the data warehouse from these various operational systems?
That's handled by a crucial process known as extract, transform, load, or ETL. Data is extracted from the OLTP databases, either via periodic batch dumps or continuous streams of updates. It's then transformed, which is a critical step. This involves cleaning the data, resolving inconsistencies, joining related records, and converting it into an analysis-friendly schema. Finally, it's loaded into the data warehouse ready for queries. This ETL pipeline is often quite complex and takes significant engineering effort.
Who typically uses data warehouses? Is it every company, big or small?
Data warehouses are almost ubiquitous in large enterprises. They're essential for companies like major retailers, financial institutions, or telecommunications providers that have many disparate operational systems and vast amounts of historical data. However, they're relatively rare in smaller companies, primarily because smaller companies often don't have so many siloed OLTP systems, and their data volumes are typically small enough to be queried effectively using a conventional SQL database or even just a spreadsheet.
Yeah.
In large organizations, unifying and making sense of data from hundreds of different sources is a monumental task that requires this dedicated architecture.
So a major advantage of a separate data warehouse is that it can be specifically optimized from the ground up for analytic access patterns, which are very different from OLTP.
Absolutely. The indexing algorithms we discussed earlier, like B trees and LSM trees, while excellent for OLTP's key value lookups and low latency writes, are often not ideal for answering the types of broad, aggregative, scan-heavy queries common in OLAP. Data warehouses are built with different internal structures that play to the strengths of analytical workloads.
It's fascinating how, even though both OLTP databases and data warehouses often use a SQL interface, their internal engines are fundamentally different. It's like they speak the same language but have entirely different brains.
Exactly. SQL provides a common language for interaction, but beneath the surface, their storage formats, indexing strategies, and query execution engines are highly specialized for their respective workloads. This specialization has led to many database vendors focusing either on OLTP or OLAP, or integrating separate engines within the same product, like Microsoft SQL Server with its in-memory OLTP and columnar OLAP capabilities, or SAP HA. You also see a distinction between traditional commercial data warehouse vendors like Teradata and Vertica, and the newer open-source SQL on Hadoop projects like Apache Hive, Spark SQL, and Impala, which are often inspired by Google's pioneering Dremel system.
Now, when we talk about how data is structured within these data warehouses, especially for those massive analytical queries, I hear the term star schema quite a bit. What does that mean?
A star schema is a very common, almost formulaic style for organizing data within data warehouses. At its center is a fact table, which represents an event that occurred at a particular time. For a large grocery retailer, this might be a fact sales table where each row represents a single customer purchase. These fact tables can become truly enormous, often containing trillions of rows and growing to tens of petabytes for large enterprises.
And then there are dimension tables surrounding the fact table, giving it that star shape.
Yes, these are foreign key references from the fact table, providing context. If a fact represents an event, dimensions represent the who, what, where, when, how, and why of that event. For instance, a DIM product table might contain details like SKU, brand name, category, and nutritional information. DIM store would have details like store name, location, and manager. Even dates and times often get their own dimension tables, allowing for rich analysis like differentiating sales on public holidays versus regular weekdays. The star name comes from the visual representation. The central fact table is surrounded by its dimension tables radiating out like rays.
And I've heard of snowflake schemas too. Is that just a fancier star?
That's a variation where dimensions are further normalized or broken down into subdimensions. For example, DIM product might reference separate brand and category tables instead of embedding all that detail directly. While more normalized, star schemas are often preferred in data warehousing because they are simpler for analysts to understand and query directly. Data warehouse tables, especially fact tables, are also typically very wide, often having over 100 columns, with dimension tables including extensive metadata.
So with fact tables that can have trillions of rows and petabytes of data, and often 100 plus columns wide, how do you efficiently query them for analytics? Because a typical analytic query like total sales by product category last quarter only accesses a few columns, even if it scans many rows.
This highlights the critical limitation of traditional row-oriented storage, where all values from one row are stored together, one after another, on disk. Even with indexes, a row-oriented engine would be forced to load entire 100-column rows into memory, parse them, and then filter out the 97 or 98 irrelevant columns. That's incredibly inefficient and bandwidth-intensive for OLAP. This brings us directly to a revolutionary approach: column-oriented storage for analytics.
So the core idea is, don't store all values from one row together. Instead, store all values from each column together. So all the date key values in one place, all the products values in another, and all the quantity values in a third, and so on.
Exactly. That's the fundamental principle. If each column is stored in a separate file or block on disk, a query only needs to read and parse the specific columns it actually uses. For your example of total sales by product category last quarter, you'd only need to read date key, products, and quantity columns. This saves massive amounts of I/O bandwidth, which, remember, is the primary bottleneck for OLAP workloads.
But then how do you reconstruct a row if all the columns are scattered across separate files?
The column-oriented layout relies on each column file maintaining rows in the same implicit order. So if you need to reassemble the 23rd row, you simply take the 23rd entry from each individual column file and combine them. The system just knows that the nth value in the date key column corresponds to the nth value in the products column, and so on. And this principle isn't just for relational data. Columnar storage formats like Apache Parquet, popular in the Hadoop ecosystem, also support document models and nested data structures in a columnar fashion.
This sounds like it would be absolutely phenomenal for compression, since you're storing similar types of data together.
Phenomenal is an understatement. Values within a single column are often highly repetitive. Think of a product category column for billions of sales records. There might only be a few thousand distinct categories. This inherent repetition within a single column is ideal for various compression techniques. One particularly effective one is bitmap encoding.
Bitmap encoding, how does that work, and how does it help with queries?
If a column, say product category, has n distinct values, like fruit, candy, dairy, you can conceptually turn it into n separate bitmaps. Each bitmap represents one distinct value, with one bit for each row. 1 if that row has that value, 0 if not. For columns with a small number of distinct values, these bitmaps can be stored incredibly compactly. For columns with many distinct values, making the bitmaps sparse, run-length encoding can make them incredibly compact by just recording sequences of identical bits. Here's 1,000 zeros, then 50 ones.
And how do these bitmaps help with queries?
They're perfect for data warehouse queries because bitwise operations are incredibly fast for CPUs. For example, where products INAS 30, 68, 69 becomes a simple, super-fast bitwise OR operation on the three corresponding bitmaps. Where products GLERV1 and STORESC includes 3 becomes a bitwise AND operation on their respective bitmaps. This works because the bits correspond to the same row across columns, allowing complex filtering to be reduced to very efficient CPU operations.
Just a quick clarification. When systems like Cassandra or HBase talk about column families, that's not the same type of column-oriented storage, is it? It sounds confusingly similar.
That's a very important clarification. No, it's very misleading terminology in that context. Within Cassandra or HBase column families, they still typically store all columns from a single row together, albeit in a flexible, schemaless way. They don't use the same type of column compression or the truly column-oriented storage layout that we're describing for analytical databases like Vertica or ClickHouse. They're still largely row-oriented within that column family.
Beyond just disk I/O, you also mentioned CPU efficiency earlier. How does column-oriented storage help with that once the data is already loaded from disk into memory?
Once data is loaded from disk into memory, other bottlenecks appear, like memory bandwidth to the CPU cache or bubbles in the CPU's instruction pipeline. Column-oriented layouts are excellent for CPU efficiency. Because data of the same type is grouped together and often compressed, query engines can process chunks of this compressed column data in tight loops directly within the CPU's L1 or L2 cache. This technique is called vectorized processing. CPUs can perform operations on these continuous blocks of data much faster than on scattered row-oriented data, leading to phenomenal performance gains. Bitwise operations on compressed chunks are lightning fast, for example.
What about sort order and column storage? Does that matter for analytical queries?
It definitely does. While data is stored by column, the rows themselves are often sorted within those columns based on one or more sort keys, for example, by date key, then products. This ordering is hugely beneficial for analytical range queries. For instance, if date key is the first sort key, queries for all sales last month will be much faster because the optimizer can simply scan a contiguous block of rows on disk rather than jumping around.
And I imagine sorting also helps with compression because similar values would be grouped together.
It absolutely supercharges compression. Sorting brings similar values together. If the primary sort column has few distinct values, you'll get incredibly long sequences of repeated values in that column, which leads to extremely effective run-length encoding. The compression effect is strongest on the first sort key, gradually becoming less so for subsequent sort keys, but it remains a powerful advantage.
And I heard some systems even store the same data, sorted in several different ways. That sounds incredibly redundant, but also potentially very powerful.
That's a clever extension, pioneered by research projects like CStore and adopted by commercial systems like Vertica. The idea is that different analytical queries benefit from different sort orders. Since data often needs to be replicated across multiple machines anyway for fault tolerance and query parallelism, why not store those redundant copies sorted in different ways? When a query comes in, the system analyzes it and picks the version of the data that best fits the query pattern, the one that's already sorted in the most optimal way for that specific aggregation or filter. It's similar to having multiple secondary indexes, but instead of just pointers, the entire column data is sorted differently, leading to massive speedups for complex analytical queries.
This all sounds great for reads and analytical processing, but if you want to insert a new row, you'd have to rewrite many column files. How do column-oriented databases handle writes efficiently if they can't just append a new row?
This is where they cleverly leverage the LSM tree approach we discussed earlier. All incoming writes first go to an in-memory store, much like an LSM tree's mem table, where they're added to a sorted structure. When enough writes accumulate, or periodically, these in-memory changes are then efficiently written out to disk as new, immutable column segments. Periodically, these new segments are merged in bulk with the existing column files on disk using a background compaction process. Queries then seamlessly check both the fresh in-memory data and the older on-disk column files, and the query optimizer combines the results to give you the most up-to-date view. It's the best of both worlds for write-heavy analytics.
So, we've talked about storing raw data, whether it's in rows or columns. But many data warehouse queries involve aggregate functions like SEM, COW&AT, or ABG. Recomputing these on raw petabyte-scale data repeatedly for every report sounds incredibly wasteful and slow.
It absolutely is. That's why in data warehousing, there's a strong emphasis on pre-aggregated data. This leads us to the concept of data cubes and materialized views. If the same aggregates are used frequently by many different reports or dashboards, why not cache them? One way to do this is with a materialized view.
So a materialized view is like a query result saved to disk, not just a virtual view that's a shortcut to a query that's run every time.
Exactly. A materialized view is an actual persistent copy of query results physically written to disk. Unlike a virtual view, which simply re-executes its underlying query every time it's accessed, a materialized view is a stored table. However, this means when the underlying raw data changes, the materialized view needs to be updated, which adds write overhead and can be complex to manage for freshness. This update cost makes them less common in OLTP databases, but they can make a lot of sense in read-heavy data warehouses, where the performance benefit for frequently accessed aggregates often outweighs the update complexity.
And a data cube, or OLAP cube, is a specialized type of materialized view, correct?
Yes, it's a very common and specialized form that has been central to business intelligence for decades. A data cube is a grid of aggregates grouped by different dimensions. Imagine a simplified two-dimensional cube for sales data, with dates along one axis and products along another. Each cell in this grid would contain an aggregate, like the sum of sales, for that specific date-product combination. You can then summarize or roll up along each axis to get totals for all products regardless of date, or total sales by date regardless of product.
But real-world data often has many more than two dimensions. Our grocery retailer example had date, product, store, promotion, and customer. Visualizing that sounds like a brain melter.
You're right, visualizing a five-dimensional hypercube is indeed hard for the human brain, but the principle is the same. Each cell in this multidimensional structure contains the pre-aggregated sales for a particular combination of those dimensions. These values can then be summarized repeatedly along any of the dimensions, allowing analysts to slice and dice the data very quickly.
The advantage being that certain analytical queries become incredibly fast because they're essentially pre-computed and ready to go.
Precisely. If you want to know the total sales per store yesterday or the total sales of a specific product category last quarter, you just look up the pre-computed total in the cube. No need to scan millions or billions of raw rows. This can turn a query that would take minutes or hours into one that returns in milliseconds. The disadvantage, however, is reduced flexibility. A data cube cannot easily answer questions that rely on dimensions or granularities not included in the cube. For example, you couldn't easily calculate the proportion of sales from items over $100 if price wasn't one of your cube's dimensions, because that data isn't pre-aggregated.
So most data warehouses probably strike a balance between raw data and these cubes.
Yes, exactly. They usually retain as much raw granular data as possible and then use aggregates like data cubes or materialized views as a performance boost for the most common high-value queries rather than as the sole source of truth. It's about optimizing for the 80% of queries that are most frequently run while still allowing the flexibility of querying the raw data for ad hoc exploratory analysis.
Well, this has been an incredible journey through the hidden world of databases. We started with the fundamental challenge every database faces.
Hmm.
Reliably storing data and getting it back efficiently, incredibly fast.
And we then dove into the two major underlying philosophies for OLTP storage. The log-structured approach, which champions append-only operations, never overriding in place, exemplified by LSM trees and stables, and then the update-in-place school, which treats disk as fixed-size pages that can be directly overwritten, best embodied by the venerable B trees.
We saw how log-structured engines are a more recent development, often excelling at very high write throughput by cleverly turning random access writes into sequential ones. And B trees, while older, are incredibly reliable and optimized for consistent, predictable performance across a wide range of workloads. Both are titans in their own right.
We also briefly touched on other crucial indexing structures beyond just primary keys, like versatile secondary indexes for flexible search, space-saving clustered and covering indexes, powerful multi-column and multi-dimensional indexes for complex queries, and even fuzzy full-text search indexes that understand human language. And we explored in-memory databases, highlighting their true performance advantages beyond just avoiding disk reads, but by optimizing for the CPU itself.
And finally, we looked at the critical divergence between OLTP workloads, your everyday transactional apps, and OLAP workloads, the heavy-hitting analytical queries. We saw the rise of data warehousing as a specialized solution for analytics, and how column-oriented storage, with its incredible compression and vectorized processing, dramatically optimizes those massive analytical queries.
And how pre-aggregation through materialized views and data cubes further speeds up common analytical patterns, effectively pre-solving the most frequent questions for lightning-fast answers.
So you might not be building a storage engine from scratch after this deep dive, and honestly, you probably don't want to. But you are now armed with the foundational vocabulary, the core concepts, and the key trade-offs to confidently navigate the complex database landscape. This understanding empowers you to select the right database for your specific application, to ask intelligent, probing questions during architecture discussions, and to truly understand what all those cryptic tuning parameters in your database documentation actually do.
The world of data storage is a dynamic, constantly evolving field. As data continues to explode in volume and new hardware emerges like non-volatile memory, promising memory-like speed with disk-like persistence, it raises a fascinating question for you to ponder. What fundamental trade-offs in storage design will become the next big challenges? Will the lines between OLTP and OLP continue to blur, or will we see even more specialized database architectures emerge to meet the insatiable demands of data? The engineering ingenuity here is truly inspiring.
It's certainly a space to watch, and one that impacts almost every piece of software we touch. Thanks for joining us for this deep dive into the fascinating world of database storage and retrieval. We hope you feel a little more well-informed and a lot more curious.